to non-innocent ligands in the CO2 hydrogenation to formate by an IR3P pincer catalyst evaluated by a static DFT. It's a long title. And it's weird. So, yeah, that's the name of my title of my article, which I understood like 5% of what's happening.
That's fine.
And pretty much what they did is they're looking ways to make other compounds out of CO2 because we have excess of CO2 in the atmosphere, and they're saying that we have like a lot of like energy deficits, and they're trying to cover like energy deficits using CO2 to get things like methanol or uric acid and stuff like that. So what they're doing here, they're taking this, there is a pyridine ring, and they're using it to, if you see in the number 1, they're introducing the CO2 to the equation, and then through a series of steps, they're doing hydrogenization of CO2, and they're getting it out right here. So from there, they're gonna make the pyridine aromatic again, to get it to be able to reactivate it to be a catalyst, to keep doing the same reaction over and over. So this other half over here is just them reactivating the catalyst and then using that H2 as a cleavage to get it to the like first form that you see on the number 1. So like CO2 goes in here, it goes through these DS23 and DS34, and then you get the hydrogenization of it, I guess. And then you use the OH to make it aromatic again, get water out of it, and then with the H2, you reactivate it to get the same form you had in the first step. So they realized that they could use a pyridine ring to do a cycle, like a full cycle, and just reuse it over and over to keep doing the hydrogenization of CO2 to get like methanols and like different like fuels that they could use, because they found out that CO2, even though it's like very like abundant in air, is not very reactive by itself. Like it's very inert. So they needed like a kind of catalyst, and that's what they're using the pyridine ring for. And that's pretty much what I got out of this paper so far.
Okay. So is the starting compound number 1, is that so the pincer, does everybody see the pincer complex portion of it? So the color coding system in the middle tells you which atoms are which. So blue is nitrogen, so that blue ball is the nitrogen in the pyridine ring, and then the pyridine ring has arms coming off of it at the 1 and 5 positions. And that's what makes it a pincer, because it's coming around and basically connecting to the metal in a couple different, from a couple different heteroatoms. You guys can see that the lighter green there is phosphorus, so it has phosphorus on either side of it. So are the balls, because my eyesight's horrible, I obviously showed my age earlier, is it starting off as a hydride? Is that what those 2 maybe balls right below the metal is in number 1?
These little tiny things?
Yeah.
They're greenish blue, like a bluish color.
So those
They look like
those
they're
are
hydrogens,
Yeah.
because the rest of
Probably
the carbons have.
Okay. So then it is a hydride complex to start off with. I gotcha. So they regenerate that at the very end. I see.
They just tried like to reduce the catalyst and just keep throwing more CO2 in it.
Interesting. This will be a good one for when you do it toward the end of the semester. It's got a lot of, again, similar steps that we'll cover, like
And
Mallory's
see,
paper did.
Down here you see how like the energy of the catalyst changed throughout the cycle.
So you said that this was DFT? They had that in the title?
They did DFT calculation.
Okay. So you guys will see some of this when we start using the Gaussian program. You can start calculating energies of HOMOs, LUMOs, transition states, etc. Yeah, we will. You have Gaussian?